Across the globe, an invisible, highly intricate physical network makes modern digital infrastructure possible. As global economies race to integrate artificial intelligence and high-performance computing, public scrutiny is turning toward the massive physical facilities required to actually run these operations. This chart tracks global data center power consumption. In 2024, these facilities consumed roughly 415 terawatt-hours of electricity, about 1.5% of global power. According to the International Energy Agency, demand is expected to more than double to 945 terawatt-hours by 2030. We have to look at the underlying hardware to understand why this trajectory is so steep. Here we see a direct energy comparison. A standard web search consumes about 0.3 watt-hours of electricity. A single complex generative AI request requires approximately 2.9 watt-hours. That 10-fold multiplier in energy draw at the processor level is the primary bottleneck for scaling digital infrastructure today. Scaling AI compute creates a direct thermodynamics problem, forcing engineers to redesign how facilities manage immense heat. To manage this heat, the industry first needs a rigorous way to measure how effectively a facility routes power directly to its hardware, rather than wasting it on external operations. The standard metric is PUE, or Power Usage Effectiveness. It measures total facility power compared to actual IT equipment consumption. A baseline score of 1.0 represents theoretical perfection, a state where zero electricity is lost to lighting or external cooling. In an older facility, energy branches away from servers to support the building, resulting in a global average PUE of 1.58. But in a cutting-edge hyperscale design, the gauge drops to 1.10, redirecting power almost entirely into the hardware. Achieving a 1.1 PUE means 85 to 90% of the facility's total electricity goes straight into the processing units. Pushing that much voltage into high-density silicon creates an immediate physical consequence. Electricity is converted into extreme, localized heat directly on the chips. Maximizing electrical efficiency forces engineers to confront the physical limits of thermal extraction. We have to get the heat away from the silicon before it melts. Water is the traditional, highly effective medium for extracting heat from heavy industrial systems. For years, data centers have relied on legacy open-loop evaporative cooling. Looking at this schematic of an open-loop system, heated water is transported away from the servers and pumped into a cooling tower. There, it is exposed to the outside atmosphere, and the heat escapes through evaporation. To evaluate this fluid loss per unit of power, the industry uses water usage effectiveness, or WUE. Traditional evaporative systems post a WUE between 1.5 and 3.0 liters of water consumed for every kilowatt-hour of electricity. Applied to a large-scale data center campus, that ratio creates a severe resource drain. These traditional facilities can evaporate between 1 million and 5 million gallons of water every single day. Relying on high evaporation cooling at the gigawatt scale directly pits data center expansion against local municipal drinking water supplies. Next-generation AI infrastructure avoids this bottleneck through a mechanical pivot to direct liquid cooling. This cross-section shows direct liquid cooling in action. Coolant circulates inside completely sealed pipes, passing directly over the surface of the microprocessors to absorb the heat. The critical distinction is that this liquid remains entirely trapped within a closed loop. The absorbed heat is transferred out via secondary mechanical systems. The primary fluid is never exposed to the outside atmosphere. By sealing the architecture, operational water loss plummets. The water usage effectiveness drops to less than 0.1 liters per kilowatt-hour. To put that near-zero loss into perspective, a 30-megawatt closed-loop facility uses no more operational water annually than a standard commercial restaurant. Shifting to a closed-loop architecture mechanically decouples the scaling of AI networks from local water depletion. Understanding these thermodynamics at the micro level allows us to examine how they are implemented at the macro level. In the Philippines, the Bases Conversion and Development Authority is currently planning the Pax Silica Economic Security Zone in Tarlac. This map highlights New Clark City, outlining the 1,620-hectare boundary designated for the PAC Silica hub. It is engineered specifically for dense AI compute and semiconductor packaging. At full build-out, the project projects a total power demand of up to 3 gigawatts. If developers applied traditional power consumption models, a 3-gigawatt load would severely compromise the local residential grid. To prevent this, the development plan relies on embedding captive clean energy directly into the infrastructure itself. Initial commitments include embedding a 500-megawatt solar farm directly inside New Clark City in partnership with Aqua Power. Sovereign infrastructure projects must construct dedicated clean energy networks to sustain immense AI loads without crashing regional infrastructure. The water management strategy follows the same localized, closed-loop logic. Official plans carry a mandate to strictly avoid drawing from local groundwater aquifers. Instead, this diagram illustrates the alternative plan, a distinct network of surface impounding reservoirs built entirely separate from the deep groundwater layers. These dedicated surface reservoirs capture and store rainfall specifically to feed the facility's minimal operational requirements. By pairing surface water harvesting with the ultra-low fluid loss of closed-loop cooling, the data center eliminates competition with the municipal drinking supply. This infographic outlines the required synthesis for modern design: high PUE efficiency, closed-loop water conservation, and dedicated clean energy. Extreme compute intensity can only be sustained through these highly specific architectural choices. The global expansion of AI relies entirely on engineering sustainable thermodynamic loops that power innovation, while rigorously protecting the foundational resources of local communities.